Alright, hello everyone. Today we're going to talk about lesson 10.7, special segments and circles. Well, our objectives here will be to find measures of segments that intersect in the interior of a circle. And we'll also be finding measures of segments that intersect in the exterior of a circle. So, theorem 10.15, we're going to get started here. Segments of chords theorem. So, if two chords intersect in a circle, then the products of the lengths of the chord segments are equal. So you can see here, it's kind of color-coded for us. Segment AB times BC, that's the intersected parts of AC, so AB times BC would be equal to DB times BE. And so you can use this theorem to find measures. All right, so as we look at example 1, we want to find x. So we need to use that theorem. So EB times BD, the pieces of the segment are equal to the products of AB times BC. That's how we use this theorem. And now, of course, we're going to plug in EB is x, BD is 10, so x times 10 is equal to AB is 5 times BC is 12. So if we solve this equation, we get, of course, x times 10, that's 10x equals 5 times 12, 60. Divide by 10, you should get that x is 6. All right, pretty straightforward there. Next one, got some expressions. Maybe it looks a little tougher just right off the bat, but we're just still using the same theorem. So we're trying to find x, so we want to use that jk times kl would be equal to, now we use the other chord here, pk times km. Okay. And we want to use this to solve. So jk is x plus 10 times kl is x. So we're going to multiply those together. I'm going to use parentheses here because it helps keep track a little better. And then we've got pk, x plus 8, times km. Oh, excuse me. pk is x plus 1, km is x plus 8. So, went backwards there. That's all right. We've got km. We just flipped it. Order doesn't matter when we multiply, so we'll be all right. Of course, now here we've got the distributive property, x times x, x squared plus x times 10, 10x is equal to, here we've got a FOIL, x times x squared, 1, 1x, 8x, and plus 8. So here the x squareds on both sides will cancel, so we've got 10x equals 9x plus 8. We subtract 9x, get that x is equal to 8. All right. So those are our first couple of examples. That property, or that theorem 10.15, pretty easy to use. You just got to use the the segments of each chord. So AB times BC, EB times BD. All right. Find measures of segments in circles. So this is how we can apply this in a real world problem here. So the true shape of a rainbow is a complete circle. Many don't know that, but the true shape of a rainbow is a complete circle. So this would, continue on and make a complete circle. In fact, I'm going to do that now best I can. Of course, the dimensions here are going to be a little weird, but we'll do our best to make a full circle. Kind of get cut off here at the bottom just because of the shape of my board here. So let's say that's a circle there. Right. However, we only see the arc of the circle that appears above Earth's horizon. Of course, we only see the rainbow part. We only see this top part, that top arc. All right. What is the radius of the circle containing the arc of the rainbow shown? So we want to use I want to find what the radius of this circle is. So how are we going to do that? Right, well, we use these as two chords. One chord is 5 miles. It's even shown that it's bisected, so we know that this would be 2.5, this would be 2.5. And let's call the segment that we can't see, let's call it x. All right, we've got 0.7 miles above, and then we got x here. So if we use that theorem, okay, if we use the theorem that we just learned, we know that the segment 2.5, if we take that chord and we multiply it together, so 2.5 times 2.5, those two intersected segments, that would be equal to, kind of running out of room here in the circle, would be equal to, I really won't need the room, I suppose, 0.7 times x, this remaining segment, x. So if we solve this, 2.5 times 2.5 is 6.25 equals 0.7x. Divide by 0.7. We get the x is, let's just do one decimal place, 8.9. So x is 8.9. All right, so this chord that is, we see 0.7 above the surface, we see 8.9 would be kind of the part we don't see. Well, that chord is a diameter. That goes through the center of our circle here. So that is a diameter. So what would the diameter be? The diameter would be 8.9 plus 0.7. That is our diameter is equal to that. So here the diameter, 8.9 plus 0.7 is 9.6. Of course, the radius is 1/2 of that. So here the radius would be, divide by 2 now, 4.8 miles. So that would be the radius of this circle here. So, hey, good problem-solving problem. Just had to use the theorem we previously learned. So I think that one's kind of interesting. Theorem 10.16, the secant segments theorem. So if two secants intersect in the exterior of a circle, so these secants intersect outside the circle, as shown, then the product of the measures of one secant segment and its external secant segment is equal to the products of the measures of the other secant and its external secant segment. So here we use that the whole secant, so we use that AC, the whole secant, times the segment that is just outside AB equals, so that's the AB segment, the whole other secant, AE, times just the segment outside, AB. So you can kind of think of it as what I like to say, whole secant times outside equals whole secant times the outside portion. Okay. So kind of think of it that way. So we'll use that to find x here in this next example. Okay, so let's kind of set it up here. So the whole secant JG times the outside portion here is just JH, should be equal to the other secant, JL, the whole secant, times, now just the outside portion, JK. Okay. I'm going to erase my margin here because now we want to see these measures. So JG, whole segment would be x plus 8. And we're going to multiply that by JH, just the exterior part, which is 8. That equals JL, the entire secant, which is 10 plus 6, 16, times just the exterior portion, JK, which is 6. So if we solve this, here we've got distributive property. We've got 8x plus 64 is equal to 16 times 6 is 96. Subtract 64. We get 8x is equal to 32. Of course, then we divide by 8 and get that x is equal to 4. This is how you can do it when secants intersect outside of the circle. Whole times outside equals whole times outside. Right? And we've got one last, we've got the tangent segment theorem. So Theorem 10.17, if a tangent and secant intersect outside. So now the last one was secant and a secant. Here we've got tangent and a secant. So the tangent and secant intersect in the exterior of a circle, then the square of the measures of the tangent, square of the measures of the tangent, so here the tangent JK, we square that, is equal to the product of the measures of the secant in its external segment. So then the tangent squared is equal to, let's write it that way. So this is when a tangent and secant intersect. So tangent squared is equal to the whole secant times the outside. I'm going to write external, but we called it outside earlier, so let's just stick with that terminology. Outside. So that's for the secant. So tangent squared equals the whole secant times the outside portion. So we can use that here in example 4. Okay. The tangent squared, so what's the tangent? QP. QP squared is equal to the whole secant, QS, times the outside portion, QR. Right? So, we'll erase those markings again. Let's plug in here. QP is 8, so 8 squared is equal to QS, the whole secant, x plus 7, times QR, just x. So here we've got 64 equals x squared plus 7x. It's a good example of a quadratic now that needs solved. So use the quadratic formula on this. You recall, to solve a quadratic equation, you need to have it equal to 0. So let's get this 64 over here. 0 equals x squared plus 7x minus 64. And recall the quadratic formula. Negative b plus or minus square root of b squared minus 4ac all over 2a. Okay, where a is the coefficient of x squared, so a in this case is 1, b is the coefficient of x, which is 7, and c is the constant, negative 64. So we're going to plug in a, b, and c, where we see a, b, and c in the quadratic formula. So that gives us x equals negative, substitute b, which is 7, plus or minus square root of b squared, so 7 squared minus 4, times a is 1, times c is negative 64, all over 2 times a, which is 1. So we can simplify, you can go step by step here. We get negative 7 plus or minus square root of 7 squared, 49, negative 4 times negative 64, that's going to be plus 256 all over 2 times 1 is 2. So x equals negative 7 plus or minus the square root of 305. 49 plus 256, 305 all over 2. Here, simplify the square root of 205. Use a decimal here. Excuse me, not 205, 305. 17.46, let's use 2 decimal places there, so negative 7 plus or minus 17.46 over 2. Alright, and then when we look at these answers, we've got x equals negative 7 minus 17.46 over 2. This answer, it's going to be negative 7 minus 17.46. Negative 24.46 divided by 2. That answer is going to be negative. Here we're talking about distances, so this answer really doesn't matter at all. It ends up negative, again, negative distance. Now we're going to do the plus version, so negative 7 plus 17.46 over 2. And that would be x equals, I'm going to have to extend here, running out of room, 10.46 divided by 2, so 5.2 around. So how to use the quadratic formula? Okay, always fun when we get to do that. So, all right, your homework 2 through 14 is just the evens here. So, thanks for watching.